Hey there, science fans! Have you ever wondered how speakers work? They seem to magically transform silent electrical signals into the sounds we hear every day. From music to movies to phone calls, speakers bring our world alive with sound. Let's take a closer look at the amazing science behind these sound-making devices. We're going to break down the process step by step, making it easy to understand. By the end of this journey, you'll be able to impress your friends with your newfound knowledge of speakers and sound waves. Get ready to explore the fascinating world of audio technology. So, are you ready to unravel the mysteries of speakers? Let's dive in and discover the scientific wonders that bring sound to our ears. Get ready for an electrifying adventure into the world of audio. Before we can understand how speakers work, let's meet the key components that make the magic happen. Each part of a speaker plays a crucial role in producing the sound we hear, and understanding these components will give us a deeper appreciation of the technology behind our favorite music and audio experiences. Think of a speaker like a tiny factory with specialized parts working together. Just like in a factory, each component has a specific job to do, and when all these parts work in harmony, they produce the final product. In this case, sound. First up, we have the diaphragm. This is one of the most critical parts of the speaker, as it is directly responsible for creating the sound waves that we hear. This is a thin, cone-shaped membrane, usually made of paper or plastic. The material of the diaphragm can affect the quality and characteristics of the sound produced. For instance, paper diaphragms are known for their natural sound, while plastic diaphragms are more durable and can handle higher power levels. It's the part of the speaker that actually moves to create sound waves. When the diaphragm vibrates, it pushes and pulls the air around it, creating pressure waves that travel through the air to our ears. Think of it like the skin of a drum vibrating back and forth. Just as a drum skin vibrates to produce sound when struck, the diaphragm vibrates to produce sound when it receives electrical signals. Next, we have the voice coil. This component is essential for converting electrical signals into mechanical movement. This is a coil of wire attached to the back of the diaphragm. When an electrical current passes through the voice coil, it creates a magnetic field. It sits within a magnetic field created by a permanent magnet. The interaction between these magnetic fields causes the voice coil, and thus the diaphragm, to move. The interaction between the voice coil's magnetic field and the permanent magnet is what makes the diaphragm move. This movement is what generates the sound waves that we hear. Finally, we have the spider and the frame. These components ensure that all the moving parts of the speaker stay in the correct position and move in the right way. The spider is a flexible ring that holds the voice coil in place while allowing it to move freely. It acts like a suspension system, ensuring that the voice coil can move back and forth without any obstruction. The frame is the rigid structure that houses all these components. It provides the necessary support and stability, ensuring that the speaker can function correctly and produce clear, high-quality sound. Now that we know the key players, let's see how they work together to create sound. Each component, from the diaphragm to the voice coil, the magnet, the spider, and the frame, plays a vital role in the speaker's operation. When these parts work in unison, they transform electrical signals into the rich, dynamic sound that fills our rooms and brings our favorite music to life. Now let's talk about how electrical signals get transformed into the physical movement of the diaphragm. This process is fundamental to how speakers work, and is a fascinating blend of physics and engineering. This is where things start to get really interesting. The transformation of electrical signals into sound involves several key components working in harmony. Remember the voice coil sitting inside the permanent magnet? This tiny but crucial part of the speaker is where the magic begins. That's where the magic happens. The voice coil, when energized by an electrical signal, interacts with the magnetic field of the permanent magnet. When an electrical signal, like the music from your phone, reaches the speaker, it flows through the voice coil. This signal is essentially a varying electrical current that carries the information of the sound. This flow of electricity creates a magnetic field around the coil. The strength and direction of this magnetic field change with the electrical signal. Now we have two magnets in play, the permanent magnet and the electromagnet created by the voice coil. The interaction between these two magnetic fields is what drives the motion. Here's the cool part. Depending on the direction of the electrical signal, the magnetic field of the voice coil either attracts or repels the magnetic field of the permanent magnet. This attraction and repulsion create a push and pull effect. This push and pull interaction causes the voice coil to move back and forth within the magnetic field. The movement of the voice coil is directly proportional to the electrical signal it receives. It's like a microscopic dance between magnets. This dance is what converts the electrical energy into mechanical energy. This back and forth motion of the voice coil is what drives the next step in our sound-making journey. The voice coil is attached to the diaphragm, a flexible cone or dome that moves in sync with the coil. Let's see how this movement translates into the sound waves we hear. As the diaphragm moves, it pushes and pulls on the air around it, creating pressure waves that travel through the air. These pressure waves are what we perceive as sound. The entire process from the electrical signal to the movement of the diaphragm happens almost instantaneously, allowing us to enjoy seamless audio experiences. It's a beautiful symphony of science and technology working together to bring us the sounds we love. So next time you listen to your favorite song, remember the incredible journey those sound waves took to reach your ears. From electrical signals to magnetic interactions to the final sound waves, it's a marvel of modern engineering. Section 4. The diaphragm dances, creating sound waves. Remember the diaphragm, that cone-shaped membrane we talked about earlier? Well, it's time for the diaphragm to shine. As the voice coil dances back and forth within the magnetic field, it also pushes and pulls the diaphragm attached to it. Imagine a swing set. If you push and pull the swing rhythmically, it will move back and forth, creating a swinging motion. Similarly, the voice coil's movement causes the diaphragm to vibrate back and forth. These vibrations in turn create pressure waves in the air surrounding the diaphragm. These pressure waves travel through the air and eventually reach our ears, where they are interpreted as sound. The faster the diaphragm vibrates, the higher the pitch of the sound. The larger the vibrations, the louder the sound. It's all about the movement. Section 5. Amplifiers, giving sound a boost. You might be wondering, are the electrical signals from our phones and computers strong enough to move the diaphragm and create audible sound? Well, not always. That's where amplifiers come in. Amplifiers are like the cheerleaders of the audio world. They take weak electrical signals and make them stronger, giving them enough oomph to really get the diaphragm moving. Think of it like turning up the volume on your stereo system. Without amplifiers, the sound from our speakers would be very faint. Amplifiers ensure that the voice coil receives enough electrical current to create a strong magnetic field, resulting in powerful and clear sound. They are essential for enjoying music, movies, and all sorts of audio entertainment. Section 6. Understanding sound waves, frequency, amplitude, and air. In this section, we will explore the fundamental aspects of sound waves and how they interact with the air around us. By understanding these principles, we can better appreciate the sounds we hear every day and how they are produced. Now that we know how speakers create sound waves, let's delve a little deeper into the science of sound itself. Sound waves are essentially vibrations that travel through the air, and these vibrations are created by objects that move back and forth rapidly, such as the cone of a speaker. Sound travels in waves, similar to the ripples you see when you drop a pebble into a pond. Just as the ripples spread out from the point where the pebble hits the water, sound waves spread out from the source of the sound. These waves carry energy through the air, allowing us to hear the sound. These waves are formed by the vibrations of air molecules. When an object vibrates, it pushes and pulls on the air molecules around it, creating areas of higher and lower pressure. These pressure changes move through the air as sound waves, eventually reaching our ears. Two important characteristics of sound waves are frequency and amplitude. Frequency refers to the number of vibrations or cycles per second, and it is measured in hertz, A's. Amplitude, on the other hand, refers to the size or strength of the vibrations. Frequency determines the pitch of a sound. A higher frequency means more vibrations per second, resulting in a higher pitched sound. For example, the chirping of a bird has a high frequency, which is why it sounds high-pitched to our ears. A higher frequency means more vibrations per second, resulting in a higher-pitched sound like a bird's chirp. Birds produce these high-frequency sounds by rapidly vibrating their vocal cords, creating the characteristic chirping noise. A lower frequency means fewer vibrations per second, resulting in a lower-pitched sound, like a dog's bark. Dogs produce these lower frequency sounds by vibrating their vocal cords more slowly, which creates the deeper, more resonant barking sound. Amplitude, on the other hand, determines the loudness or volume of a sound. A larger amplitude means that the air molecules are vibrating with more energy, which results in a louder sound. This is why a loud shout has a larger amplitude than a quiet whisper. A larger amplitude means the air molecules are vibrating with more energy, resulting in a louder sound. When you hear a loud noise, it is because the sound waves have a high amplitude, causing the air molecules to move more forcefully and create a stronger sensation in your ears. A smaller amplitude means quieter sound. When the amplitude of the sound waves is low, the air molecules are vibrating with less energy, resulting in a softer sound. This is why a whisper has a much smaller amplitude compared to a shout. So, when you adjust the volume on your speaker, you're essentially changing the amplitude of the sound waves being produced. By increasing the volume, you increase the amplitude, making the sound louder. Conversely, by decreasing the volume, you reduce the amplitude, making the sound quieter. Understanding these basic principles of sound waves can help us appreciate the complexity and beauty of the sounds we encounter in our daily lives.